Okay, here is a problem based on Hess's law. We have this reaction. Calculate the standard change in enthalpy delta H for the following reaction. So this is a very slow reaction, and it's not very practical to carry out this reaction at room temperature. So this is the direct path. This is direct, and let's say that's slow, difficult to measure the enthalpy change. So instead of carrying out this reaction, which is slow at room temperature, not so practical, we can carry out the same reaction in 3 different steps. So according to Hess's law, the enthalpy change of this reaction should be same as the sum of the enthalpy changes of these 3 individual reactions. So enthalpy doesn't really depend on the path. It's independent of the path. That's why it's called a state function. So before we calculate the enthalpy change for this reaction using these 3 individual reactions, let's rearrange these 3 reactions. So when I rearrange these 3 reactions, I should be able to derive this reaction. And just a couple of things. So when I derive this equation using from these 3, we just have to make sure that the same things are on the same side. Like if I have C2H6 on the left, and here I have C2H6, here should be on the same side, which is left. And we also have to make sure the coefficients are the same. If the coefficient of C2H6 here is 1, I have to make sure that's 1 as well. So let's rearrange these 3 equations to get this equation. So in my original equation here, C2H6 on the left hand side, and here it's on the left hand side, that's fine, but the coefficient is not the same. So I have to make sure this coefficient is 1. So what I do is I divide the first equation by 2 to make that coefficient 1. So let me rewrite that. So when I divide the first equation 1 by 2, this is what I get. C2H6 plus 3.502, because we are dividing by 2. 4 divided by 2, that's 2CO2, plus 6 divided by 2, that is 3H2O. So, and we also have to divide that delta H by 2 as well. That becomes negative 1560 kilojoules. Right? That's what we did. We took the equation 1 and we divided by 2. Let's take a look at the second equation. So in the second equation we have hydrogen H2 on the left, and here we have hydrogen on the right. So we have to make sure this hydrogen and this hydrogen are on the same side, and also the coefficient should be the same. The coefficient here is 1, that's 2, so we divide this by 2. So we're saying this hydrogen and that hydrogen has to be on the same side. So to do that, what we do is we flip the second equation. So we flip, that is one thing we got to do, so that this hydrogen comes to the right hand side, and since the coefficient of hydrogen is 1 here, and since it is 2, we also divide by 2. Divide by 2. Let's do that. So for the second equation, we flip and divide by 2. So when I flip, the water comes here, and I'm dividing by 2, so that would be H2O, liquid, becomes H2 because I'm dividing by 2, and that would becomes half O2 gas. So since I'm flipping this equation, this delta H sign becomes positive because we're flipping this. So negative 572 becomes positive. So the negative sign becomes positive since we flip, and we're dividing by 2. So 572 divided by 2, that's 286 kilojoules. Right? So now we have the H2 here, and in our parent equation on the same side the coefficients are the same. Let's take a look at the last equation, the third equation, C2H4. So we have C2H4 here in the third equation. We have C2H4. They have the same coefficients. But here our C2H4 in this equation is on the right hand side, but here it's on the left. So we got to flip this. So equation 3, flip. Just flip. So when we flip that, it becomes 2CO2 plus 2H2O gives C2H4 plus 3O2. Since we are flipping that, the delta H sign is also flipped, so that becomes positive 1411 kilojoules, right? So we have rearranged these three equations, and our goal was, when I add these three equations, I should end up with this equation. So let's do that. So before I add these three equations, let's cancel out the identical terms. So I have 2 moles of water plus 1 mole of water on the left hand side, so altogether that's 3 moles. So 3 moles of water on the left hand side will cancel out with 3 moles of water on the right hand side. And I have 2 moles of CO2 on the left, that cancels out with 2 moles of CO2 on the right. What else can we cancel out? That's 3O2 plus half O2, that's 3.5 O2 on the right. So 3.5 O2 on the right can cancel out with 3.5 O2 on the left. So we cancelled out the identical terms, and let's add these three equations, whatever is remaining. So we have C2H6 left on the left hand side, nothing else. We have cancelled out the remaining identical terms, and we have just C2H4 from here, and we have H2 from here. So essentially we derived exactly the same equation by manipulating and eventually adding these three equations. So but we have the most important task here. We are not done with delta H. So since we added these three equations, we have to add these three enthalpy changes. Let's add that. So that would be delta H would be, if I add the three delta H values, that would be, my final delta H would be negative 1560 kilojoules plus 286 kilojoules plus 1411 kilojoules. So if I add them together, so the total sum should be about positive 137 kilojoules. That is the total enthalpy change that takes place when ethane is converted to ethene and hydrogen. As we said at the beginning of the video, that it's a slow process. It's not very practical to carry out this reaction in a single step. Rather, we can carry out the same reaction in 3 different steps, and if we add up the individual enthalpy changes, that should be equal to the enthalpy change of the reaction that can take place in just one step. So that's Hess's law. So according to Hess's law, the enthalpy change does not depend on the path. So it's path independent. That's why according to Hess's law, enthalpy is a state function.